Just double check. Cool. All good? All right. Cool. All right. Thank you, everyone, for your patience. I'm very excited to introduce Rodrigo Constanzo for our next Augmented Instruments Lab seminar. Rodrigo is an artist and a musician and a technologist and a researcher and many more things. He's currently based at the Royal Northern College of Music, where he teaches in the popular music program there, and does lots of really interesting stuff with music and technology and Max MSP and machine learning, and really excited for this presentation. So thank you, Rodrigo.
Cool. Yeah. Welcome, everybody. Oh, not welcome. Thank you, everybody. Yeah, let me scroll past this. So a little bit about me. Jordy said some stuff, but just to kind of add, I'm a performer, composer. I put in brackets there, improviser. I put brackets there just because I guess at this point in my life and air quotes career, I don't really consider myself that anymore, though that was, I guess, my field of study when I did my PhD. I do luthiery in terms of like, I don't make like violins or anything like that, but I make a lot of instruments. I'm going to be talking about that today as one of the main things I do, but this spans both hardware and software based things. My PhD was music composition. I teach for a living, do a lot of workshops and that kind of stuff. And in general, I'm, that's me with my first piano when I was a little kid. So what I'm going to talk about today is two strands. So one is this broader like meta instrument approach that I've been doing over the last few years with drums and augmented objects and things on it. And the other one is a specific work in progress that I'm working on at the moment on triangulating position on a drum. So there'll be the two kind of branches of it, and then obviously some time for questions and stuff. But before I get going, I always find it useful to just play a bit of audio to calibrate people's expectation and just where I'm coming from musically and artistically, the kind of things I typically do. So I'll just play a little bit of a video here of just some performance stuff, just to give you an idea of what that's about. And so on, but that's just to kind of give a rough idea of where I'm coming from creatively, aesthetically, and that kind of stuff. So that there, people have questions about that, I can talk about that later on, but that's using a lot of audio descriptor analysis, a lot of audio analysis, sending things to corpus matching and some CV generation for a synth. So all of that was essentially happening in real time just from the audio analysis of that microphone that you see there. All right, so what I'm going to talk about is this like meta instrument kaizo snare approach to specifically drumming that I've been doing over the last, I don't know, maybe 10 years at this point. So this is what my drum looked like maybe a year and a half, 2 years ago. So I've got a snare drum with a bunch of 3D printed things on it and a bunch of DIY controllers. This is some of those things labeled, which I'll talk about and explain in a bit more detail shortly. But as of last year. It's actually changed a little bit more since then. This is what my setup looks like now. So I have a gong drum, so a 22-inch gong drum, all manner of things attached to it, sort of a airy touch, like a force-sensitive kind of thing up top that I play with sticks, and then a bunch of controllers attached to it. So this is closer to my setup now. So I want to kind of talk, before I unpack the things, like how I ended up at that position, like how did I end up with these specific instruments. So I grew up as a pianist, then a guitar player and drummer last, but before I moved to the UK, maybe like 15 years ago, this is what my setup looked like. I had a 4-piece kind of jazz-sized drum set with a lot of cymbals, a lot of cymbal stands, a DIY stringed instrument to the side, some objects on the floor, but it was like, this is the peak of my maximalist setup. I added a lot of, I wanted a new sound, I would add a new acoustic source to my drum set. And this just kept expanding to the point that it was this big spaghetti mess of like hardware and sound making objects around me. Then fast forward a couple years later, I ended up with this like 3-piece set with a sampler, the string instrument still there, a few objects on the floor, some synths and stuff like that, much less cymbals, but the setup is getting pared down. Fast forward a couple more years later, I end up with this 2-piece setup, still a sampler, still some cymbals. The string instrument has shrunk down to this like 1-tier unit. There's a kind of whisk thing off to the side that I kind of made, which is interesting, which I won't talk about today. And at this point, I already have a laptop in the mix, and there's some software running alongside of everything else. So it's been this kind of trajectory of shrinking down. And at this point, I'm actually pleased that I don't remember the actual quote, but I do remember there's this Alvin Lucier quote where he talks about the act of composition being an act of removal, where when you remove one more thing, it's no longer the thing that it was. And I really like the poetics of that, like this process of, it wasn't the through line that I saw when I was doing this, but looking back on it, I can very clearly see that I removed things that weren't essential and eventually ended up at a drum with stuff stuck to it. So there's some things here that I guess like apply kind of generally, but have underpinned a lot of what I think about when I'm thinking about instrument design and software design. And one of them is this idea that I put here is like the drumstick problem, as in like when I'm playing an instrument, even though I'm doing a lot of things with software, I still, I guess, fundamentally think of myself as a performer or instrumentalist. So my hands are usually busy doing something else. Drumsticks are particularly bad because you kind of, they occupy the whole of your sort of fingers. But I want to be able to do stuff and control things. And for me, a controller nightmare would be like a fader bank. I don't have the mental throughput and physical throughput to manipulate reverb, decay time, pitch, something or other. That's like superfluous to my capacity and interest in real time. So how can I do stuff with what I can manage in real time? This idea of finding complexity and simplicity, like audio analysis, what can I do with an envelope follower? What can I extract from minimal input? This idea, which I've borrowed from my old supervisor, P.A. Tremblay, of recycled virtuosity. So being an instrumentalist, or even with gamepad stuff. Is there water by chance? Yeah, thank you. Being able to repurpose skill sets that I have. So in this case, being able to play drums, I want to be able to like access and use some of this gestural language that I have encoded in my physicality, but with software tools. How can I do that? How can I create mappings between these things? I won't, belabor each of these points, but metaphor is a mapping mechanism, like this idea of turntablism, which I will talk about some, and some other points here. So these kind of underpin some of the things. Now, it does say individual components, but so a big shift for this was this, when I started doing things with friction with a microphone. So this is it's a 3D printed housing, so it looks bigger than it is, but it's just a really cheap lapel mic, very similar to what I'm wearing now. So at the time before I could afford like a DPA microphone, I wanted some kind of Omni mic that I could clip onto my drum for live sampling purposes. Did some Googling and I found these like $40, $50 kind of cheap lapel mics. And I bought one and had it clipped on my drum. Thank you. So because it was an inexpensive mic, it meant I was also not very precious with it, which across many gigs and across many performances led me to explore things of taking this microphone and what if I like moved it around a bit. And while I was playing it, I used it as like a dynamic source. And that was kind of interesting. And then like at some point later, I'm like, what if I got it really close to the thing and started? And then eventually after many iterations, I was like hitting the drum with it and rubbing the drum with it and using it as like an actuator. And that led to a whole performance practice where I used the microphone almost as like a microscope dynamically, both in terms of like nearness to a source, but also like physically as an actuator, you know, friction and all this kind of stuff, which led to, yeah, a pretty big part of my performance practice. I'll just play a little bit of a video here from a performance using some of that. And so on. Okay, so that formed a big core of a kind of performance practice of using a microphone as not only as an input capture device, but as a gestural object in and of itself, which has infinite, in my opinion, explorability and depth to that. And then off the back of that, I got into this idea of some of my interest with that was also parallel with like the idea of turntablism and going back to this idea of recircle virtuosity and like technical proficiency with digital instruments. I got really into the idea of applying some turntablism, like, you know, scratching DJ kind of thing, as a metaphor for physical exploration of a semi-novel instrument. So I can use the microphone in my left hand, and because the drum set is round, and some of the gestures of moving and pushing and pulling can be mirrored to what one does like with scratching, DJ scratching. I could learn scratches, like an actual like DJ scratch, like trips and flares and all these things. Even though I don't have a record and that isn't the same, I can apply some of these things. So the incorporation of a fader, this is a 2.0 fader, which it's got a trill on it and some other things, which I'll show in a moment. But it enabled a kind of gestural language that was afforded by the metaphor of turntablism through the vehicle of drums. So it's like a couple layers nested of using an instrument, but with a mapping metaphor. And then there's a technical language that I can try to incorporate into my own facility. So that led into this fader thing. So this is like a fader 2.0. It was recent at the time of kind of putting it together. I've expanded also a little bit more, but I wanted to have a fader that I can use and do these gestures with. I incorporated a trill in parallel, thinking that I could do, because with any kind of fader or knob-based thing, it can't be in two places immediately after each other. Like I can't move from here to here to here within an instant. Whereas with a metaphor of a trill, if I do this, it's gone from 0 to maximum in an instant. And I can do things that are like impossible with a fader. So my thinking was that I can do kind of analog gestures above and then sort of digital gestures below, which I really do like as a metaphor. There were some fadings here in that, like, for those of you who have done things with DIY gamepads, like as in using DIY analog controller, the dead zones in there are very poor and all this kind of stuff. So I ended up refactoring this a few times with like a better Hall sensor for the analog joystick. And then I ended up with a very fun deep dive in that this fader here is using it's a rain magnetic fader. So there's 2 Hall sensors and a magnet embedded in the fader. And Hall sensors are great for position, but they fall off exponentially, meaning that the resolution was really good here, and the resolution was really good here, and the resolution was absolutely terrible in the middle, which meant that like I could do all these kind of cutting gestures, but when I was in the middle, I had like a physical resolution of one step was like almost like 5 millimeters, which was kind of unusable. So in the context of like DJ mixing is what this product is designed for, that wasn't so much an issue, but it wasn't good enough. So you can kind of see there that like there's a Hall sensor there and a Hall sensor there, and then that's a magnet. So this whole area here ended up being a bit of a dead zone. Not dead zone, but very poor resolution. So I was like, okay, I'll just put another Hall sensor in the middle. and that actually improved the resolution. But then I ended up with a new problem where the Hall sensor in the middle has no idea of polarity. So as in, like, if I'm this far away and if I'm this far away, this Hall sensor in the middle is reading the same value. So that I was still subject to the poor resolution here because I was dependent on that. And in the end, I had put 2 additional ones. So I had 4 Hall sensors in this thing, and then I wanted to be accurate, so I set up kind of glue tacked and manually made a table every ½ millimeter and plotted the actual. So you can see the outer, the yellow and the blue are what the readings from the original Hall sensors were, and you can really see this really big poor resolution dead spot. And these are the additional ones. So there's probably a way to do this mathematically within that, but I did it as a lookup table to kind of arrive at a high resolution thing. Some of this chasing of precision dragons or demons or whatever I write, though, it isn't so much that I think that like having a high resolution fader for this kind of gestural language is that important. It was more because I'm doing a lot of stuff with feedback and signal feedback, and I think landing on MIDI value 64 to MIDI value 65 is a very crude jump in the case of signal feedback. So I wanted to have high resolution points of stability with that. So when I moved the fader to the middle, I could be at a much more granular feedback stage for that specific kind of playing. One of the things which will actually be relevant to the second half of what I'm going to talk about today was this capturing higher resolution data from the drum. So for those of you that might have played drums or had drum triggers, a lot of old school drum triggers are a contact microphone or piezo-based thing, where it's usually a foam thing pressed up against the head. And this gives you decent onset detection. It gives you okay audio analysis descriptors. But my biggest issue was that it actually damped the sound of the drum. It was like having your thumb on the edge of the drum, and it actually just made the drum physically sound worse in order to capture the audio from it. That wasn't great. You can have a directional mic, a DPA 4099 or something on it, that works really well, but then you're subject to mechanical noise for false triggers. You're subject to bleed from other instruments. So my solution was, initially I used a sensor from Sensor Percussion, which is it's just a guitar pickup. It's an inductor-based thing, and you put a metal dot on the drum. This works fine, but they're expensive. Excuse me. And it turns out quite noisy in terms of signal-noise ratio. Because they're not meant, the original use case for them is they use them just for classification and not for really descriptor analysis, such that the noise floor is quite poor. So if you listen to the audio quality of one, it's very hissy. So after a bit of a lot of testing and looking around, I found these sci-fi pickups that are meant for polyphonic guitar purposes, but they end up being single capsules that are active pickups, shielded, really good signal-to-noise ratio, very flat signal, which is also unusual for guitar pickups. And I ended up building and designing a 3D printed enclosure around that. So that's a bunch of the designs and prototypes. That was an early version of it. It looks more like this now. So this I can mount on the drum. I put a metal dot on the drum, which you can, well, you'll see in the photos in a moment, but there's the pickup underneath it. And this gave me a few things. It let me get audio from the drum that's isolated from audio-based sounds, because it's an inductor-based thing. The signal-to-noise ratio was great, and the signal frequency response was very flat. Excuse me, which was also good for descriptor analysis. So that's what it looks like mounted. I then did some fork tests of that, trying to do an optical sensor, which is, comes with its own issues that that ended up not really being viable. I think it might be something to explore later on, and maybe with either as a bespoke or high power like this. I was using a single chip LDR kind of thing, and it just the amount of motion you needed to get meaningful signal it wasn't working out too well. But it's something I want to return to as an idea to explore, to have not need a physical dot on the drum. But that ended up being a kind of a failed experiment. Then there's some other components here which I'll kind of fast forward through a bit more quickly. Jeez, sorry. So additional controllers attached to the drum. This was the start of my 3D printing, CAD oriented things. As it turns out, not a lot of company makes small MIDI controllers. I don't know why. So I used this really crappy Novation thing, made some other 3D printed things. This is an interesting one, which I'll fast forward through because I want to get to the other bits. But it's using a rotational Hall sensor for high resolution position and capacitive touch for like a kind of virtual turntable kind of thing. And some other stuff. I'll skip through a bunch of things, but I'll just kind of show you some of these pictures of other additions because I want to jump to the second half of stuff here. Which is, all right, we're here. Please. So this is a current work in progress thing, which now I think is working pretty well, of being able, one of the things that is afforded and enabled by having these DIY sensors is that they're fairly inexpensive to make. So I was able to create this setup where I have 4 of these sensors, which would be a bit expensive if you wanted to buy the sensor percussion ones, mounted on a drum. And then the idea would be to be able to tell exactly where I'm hitting the drum on this. So there's some existing research on this. So there's a great paper from Sokolovsky's, I don't know if I'm pronouncing that, and Andrew, where they did a paper in 2014 using optical sensors on a drum to use, be able to determine something very similarly. So to very briefly kind of summarize their paper, they use time difference of arrival in a way that very similar to what you do with GPS satellites. So you get a timing and it arrives, you're a such distance from a satellite, such distance from another satellite, and you use some math to figure out where you are. And this is just how GPS stuff works in general. But the idea being that if I have one sensor here, and then my time difference is such between them, it means that the strike could have happened anywhere on a hyperbola between those 2 points. So with just 2 sensors, you can't tell your absolute position, but you can tell where you are on an arc between those 2 sensors. Now, if you combine multiple sensors, about sensor 1, sensor 2, that gives you 1 hyperbola, and then 2 more sensors, that gives you another one, and therefore the intersection of these points is where the strike is. So that's the core idea of the paper, and which is, I guess, fundamentally how GPS works, in our daily lives. And that gives them some kind of results like this. Now, in the paper, they did have some hyperbolas just that didn't intersect. And there's some reasons for, I think, why that's the case, but that's the sort of the summary of the paper. I'm dying of cough now. So I use that as a jumping off point to kind of build from. So the first thing was incorporating these inductor-based sensors as opposed to an optical sensor. That enabled easier real-time stuff, less signal, much better signal to noise performance, and much sharper transient and onset detection. So my first setups were this. I literally set up 4 sensors. I put some dots on the drums just as a point of reference, and I did some recordings. Now, just to kind of show you context-wise what that means. So if I hit the drum here, so near this north sensor, and this is what the audio looks like across those channels. The north sensor being this one, so that you can see the peak here. This is the east and west sensors, channels 2 and 4, and the south sensor. So you can kind of see very clearly where the peaks are displaced. So this is ultimately what's being measured, and the difference between them is what encodes where you physically are on the drum. So depending on where I hit on the drum, the relationship between these peaks would be different. Okay, so one of the things as a paper is in order to compute how the speed of sound through this membrane, you need to compute the speed of sound through the membrane. So they use this formula from Physics of Musical Instruments, which I think is a good resource for that. However, in the testing when I was doing that, when I plugged that into our tests, so that gave us a speed of sound of that, so 135 meters per second. That was working, but it ended up giving me a lot of hits that were either out of the drum or a lot of intersections that just didn't intersect, which is consistent with what was happening in like the paper. So in doing some kind of practical measurements, like, okay, I know the sensors are these far. If I hit the sound here, I can from that deduce how fast the sound is actually traveling through this membrane. And in doing that, that arrived at a different constant than what that formula would have gave us, which is actually closer just to 2 pi r, which was unexpected, but using that as a basis, it meant that we can end up with something like, actually as a point of reference. So this is what a set of intersections would have looked like using the formula from the book. It would have put the drum hit out here outside of the drum. And some of these hyperbolas don't even intersect at all. So it ended up really distorting the space because the sound is not moving at the speed that it seemed like it should be moving. When in effect, in applying what the measured speed of sound through the membrane was, it put the drum hit here, which in this case was correct. So I think there's something, and I don't know if this is, I didn't read enough of the book and I don't really understand enough about physics, but I imagine not only do you need like the fundamental frequency, the diameter of the drum, but perhaps the mass and some statistics about the sort of thickness of the membrane, whether it's coated or not, whether it's mylar or not, or whatever it is. So there's probably like a more physics-oriented way to arrive at that. But I found that just from computing it from just the measures. So that was one of the first things that made like a massive difference. Then beyond that, the initial tests were literally just plotting. So taking the measurements, put it into Desmos, and sort of, this is what that quadratic says it should be. I'm not a maths major, so this was like, you know, pushing a little edge of my knowledge, but it did prove that this was working. Another thing that, there's some kind of info in there, but one of the other things that I found is that in the original paper, they used 6 sensors, which I think is really good because it gives you good spatial resolution. But it does mean that all the further sensors tend to give poor data. And one of the things from this closed form solution of having quadratics solved is when you're incorporating values that are a little bit noisy, it tends to throw everything off in a pretty chaotic way. So another thing that helped here was only solving the nearest sensors. So if I, excuse me, hit the drum here, I only solve the time difference between these 2 drums and ignore these 2. And that also made a massive difference in that, like, not only was the speed of sound a bit more consistent, I only solved the ones that were physically nearer. So that was the jumping off point, and that worked and built that working. And then eventually ended up building a version that, one of the sad things about Max is that like you can't call NumPy to do math, you know, like, so a very, very early version of this was doing, so what this video I'm about to show here is using a Max patch for onset detection. I believe I'm using inter-onset timing, so the timing difference between the onsets arriving, and then jumping over to Python and then coming back. And that gave me, so this is me hitting the drum, moving from dot to dot, moving north. So this is real-time analysis going to Python and back. Which is pretty spot on. And you know, like as I near the edge of it, the resolution you can see, like I'm a little bit further off the point. I'm not a robot, so I probably do play a little bit off the point, but the resolution got a little poorer as I moved out to the edge. But it was working. It was a proof of concept. I was going to and from Python. Real-time wise, this was like still within like going to Python and back was, you know, incurs some latency here, but like we're talking like 5 milliseconds, 6 milliseconds from an onset detected to getting a solution. So that was like, that's viable. Going to Python and back, maybe a little less, bit more friction there that's wanted. This is what all of that would look like if it was plotted. So one of the things that, in order to bake this into doing this in Max natively without calling or solving quadratics, was to pre-compute lag maps. So instead of solving the quadratics, I would have for between south and east sensor, each unique color here you can picture as being a hyperbola. So here's a sensor and there's a sensor. So this particular yellow is the pre-solved of what that difference would be. And then basically just pre-rendered these matrices of what the solutions would be. And then that leads to something that is happening actually in real time in Max. So this is, I load some lag maps. And what's happening in here is that I'll hit it to play again. So the lag maps are pre-rendered. And then here you can see the 2 pairs of hyperbolas, what they are doing. So this isn't computing the hyperbolas. This is solving, just pulling from the lookup table of the lag maps and then the intersection. So if I play that again, This is I'm using here cross correlation, which I'll talk about in a moment, but I'm using a cross correlation window of 128 samples. So the latency here is on the order of like 2.5 milliseconds. The actual doing those lag maps and computing the centroid of the overlap, it does almost take a millisecond, which is a bit unfortunate. But like overall here, we're looking at like 4 milliseconds latency from audio to position. And it works even for like a random. So that's operating on audio in real time with a latency on the order of like 3 or 4 milliseconds. So that was one thing. And then there was a whole thing. So in the paper, the original paper, they do inter-onset timing. So you onset detection on each channel independently, and then that gives you a time, and then you compute the difference between those times. In the paper, it suggested that cross-correlation might be viable. With the optical sensors, the noise floor was so poor that it just produced garbage results. But with these signals, it was possible. So in that second video I did, I was using cross-correlation. Now, the difference here being that with inter-onset timing, I'm doing independent onset detection and then determining the difference between those, whereas cross-correlation will take the windows and align them. So cross-correlation theoretically would generally be better and actually does work very well for these signals. The one issue that I found with this was that it was a little fragile to, well, obviously the windowing, but there's a physics-based thing that I didn't know or I didn't really encounter as clearly. So here's 4 waveforms. Now there's actually, I'll show this first. This is a Roland patent from '99. So I think when they first did a mesh-based virtual or drum head, they had, I think, a contact mic cone in the center, and then I think one near each edge. And they had a crude way of approximating where you hit on the drum, because relative to where you are near the sensor, the first zero crossing encodes that information. So the closer you are to the sensor, the smaller the first zero crossing was, and the further you were. And I've tested this just as a descriptor, and it actually is fairly accurate. Like you have to do some filtering to get it so like the signal's a bit more smooth, but this phenomena is very real. So this here is if I strike the drum at the center, this is all 4 waveforms, what they look like on the optical sensor. We have a bit of a pre-ring. The red line is where the onset is detected from the onset detection algorithm. And then you have the peak. So you can see they all kind of align. They're phase correct here, but the phase could sometimes be inverse. It doesn't really matter. But this is what happens if I hit near the north sensor. So here, blue is the north sensor. You can see the pre-ring is there, but it's smushed. And here, the yellow and red are the east and west sensors. So the same pre-ring is there, but kind of extended. And the green is the pre-ring for the furthest sensor. So the peak is not even in this window. So cross-correlation, although it works, in order for it to work accurately, you need a window size that is proportional to the furthest distance you want to capture, plus the amount of distortion that might be present. Meaning that you're looking at an order of magnitude of like 512 or maybe even 1024 in order to really have that be locked down accurate. And it was quite wild to see that. I think there's probably something that can be optimized with this in terms of having where the onset is detected versus the peak but ultimately this pre-ring phenomena of the membrane and how it actuates is a physical limit of this way of measuring things. So the cross-correlation worked very well, but became fragile to needing an overly big window size. There is still some meat on that bone, and that I think, particularly for that friction-based stuff that I was doing earlier, I think I can still do cross-correlation with a rolling window to tell where I'm physically touching the drum and moving my hand around in real time. But that's a separate matter. So with that, it rewound me back to using inter-onset timing. Now, inter-onset timing is also subject to this, meaning that, I'll just use this picture of the drum, but there's a sensor here. If I hit here, the pre-ring is short, but the further I am away from the sensor, the more time slows down. So the speed at which sound travels through the membrane becomes slower the further you go in a non-linear way. So from every sensor, it slows down as it moves further away. And this is different for every sensor. So like it's not linear across the drum. It's proportional to the source of each sensor. So one of the things that I thought a buddy of mine suggested was this idea of, okay, rather than trying to learn that or build a lag map or encoding that information in, like a closed form solution or something like this, what if we just like run it into a neural network? We'll give it the lag map at a certain position. We'll give it what we expect that position to be. And hopefully the network can learn that non-linearity. And it turns out it can. So the current version I have now, with the help of Jordy here, is taking and after experimenting with cross-correlation, sending the difference of time arrival between sensors or just sending the raw arrival time of sensors, what I found worked the best was sending the order of arrival of samples. So if I just play here, like we don't need to hear the audio, but these 4 things here. The first one is cross-correlation. So this is the cross-correlated values for each of them where they should be. The second one is the, if I just stop audio arbitrarily somewhere. So this first one is cross-correlation. That's probably technically the most accurate. The second one is the inter-onset timing difference. So these numbers are kind of near each other. So like -14 to -24, -6 to -11, -2, like they're closest to what they would be, but this is from onset timing. And then this last one is what I'm actually using. The nearest sensor arrived at time 0. The next nearest sensor arrived at time 24. This is samples. The next one at 30 and the next one at 32. So these are 3 representations of the same data. This was the dumbest. I'm literally just starting a timer when I receive an onset, count when the next one arrived, count when the next one arrived. So that was computationally the simplest to do, and it encodes similar information. So I'm taking these 4 numbers. These 4 numbers, I say, that corresponds to position XY on the drum. And I give it examples of this. And that gives me, so in this case, I can run it all at once. But that picture here of where I have my drum with a 20 millimeter grid across the whole drum in like a Cartesian XY thing. These are my inputs. I have 8 hits on every one of these. And I've trained it on a subset of that data. And if I then send those all at once, this is what I get. I'll play this as audio as well, but you can see the clustering is there. You can see there is a little bit of weird nonlinear distortion near the edges where this is not a square, it's a bit more of a circle. I think there's probably something that'd be optimized for that. There's probably something to do with the tuning of the head. Maybe a certain lug is a little different, but this resolution is way better than what I got with the cross correlation. It's orders of magnitude better than what was possible in the paper. And this is effectively instant because now the latency is proportional to the longest. So the moment I receive this number, I can compute. So in this example, I have a latency of 32 samples. Well, then plus the neural network solving, which is like microseconds. The longer the window, so if I'm further in the drum, the center hits would be the slowest because that's the furthest from any given sensor, depending on where you hit. So latency-wise, we're here at like almost nothing. So if I run this with real-time audio, so I'll just put this to, yeah, I'll play this one. So this is me hitting the center of the drum and then hitting like in front of each of the lugs. The lug ones are the trickiest one because I didn't encode this information in the model. So I think if I have a more thoughtful model of what I train the network with, but you can see the clustering is still pretty good. And this is data that's actually physically outside of the grid. And again, real time, just from the 4 sensors. So the fact that this is being computed with inner onset timing, so onset detection is fairly lightweight and fairly, it's a nice onset detection. So I'm using an amplitude-based differential onset detection, which is very accurate. It's fairly low CPU. The neural network is fairly lightweight, particularly since the size of these models and varies a little bit, but effectively it's just 4 onset detectors and a neural network is the whole of this topology. my goal here is to run this on like a Bella Mini or something like that and just have this be an embedded thing. Because this works great, I can set up with a sound card, but now you need 4 channels of your interface to do it. And that's fine, but like that's a lot of I/O real estate on an interface. So the idea would be that you would just run these into your Bella. Out you would get a Cartesian or a polar representation of this data, and then you just go on from there. So that's basically a kind of a summary of all the journeys of computing this differently, solving closed form, cross correlation, inner onsets, lag maps, neural networks, and all of that. And there's a couple more things in the way. I've did some experiments with different sensor array. The reason why this drum has so many dots, I've done testing with like 3 sensors just here. Didn't work. I've done 3 sensors like this, and okay, but the resolution gets poor elsewhere. But I did a bunch of experiments to find 4 seem to work pretty well, and it isn't too onerous. The idea would be that you would then mount these internally in the drum, and you wouldn't they wouldn't obfuscate your play at all. And these are the same sensors that I actually use for classification, audio descriptor analysis, and everything else in what you heard earlier in the video. So you sort of get all that stuff for free as well. And I think that's the kind of the gist of wanted to talk about there. Yeah, that was the demo patches. Oh, actually, let me try showing this. It did kind of crash earlier, but a cool use case here is I can take, so this is a neural resonator plugin, so I can take this position data, plug it into here, and I think that's all I need. Yeah. Okay, so I turn. Okay, so here I have a physical model. So this is a neural resonator plugin. I'm sending, in this case, the position data of where I'm striking the drum. Let me pick. Yeah, so this is I'm doing the cardinal one. So I'm moving from center to north, center to east, center to south, center to west. So that'll just be playing in the background. So if I open the plugin back up, I'm actuating this model. That specific example is a bit subtle. Let me. Yeah, that's pretty good. And I can actuate and engage with like physical models, but using this as a position attribute. And I can then, I don't really understand enough about this stuff for the alpha and beta, but I could like also take descriptor analysis and take my spectral centroid or loudness or other features and use those features in addition to modulate parameters of the model. But ultimately here I'm using, because a specific plugin exposes the X and Y positions of your point of actuation, I'm using that to actuate this model in a different way. So this is one of many, I think, quite compelling use cases for this kind of thing. And particularly with this model, because you can, compute that all dynamically as well. So that is the kind of the bottom of that bit. So, questions? Oh, yeah, so.
Hi, I've seen it's great work, really cool. But I wanted to ask you about some of your previous work, or well, it's related to this work as well. I've seen some of the things you've done with practice research and like video annotating tools, and here it's very clear that you follow some sort of like diaring or a way of tracking. How did you do it? Because I find it really hard I try to do those things, but I find it really hard when there's lots of like trial and error to actually keep track of things and not interrupt the work. So how are you managing that?
Yeah, so with some of these parts, this one was tricky because this spanned, like this second half of the talk spanned like 2.5 years of start-stop. Like I'm intensely and then not looking at it for 6 months. So this one was particularly tricky. I had to go back through tons of emails. Thankfully, all this stuff, I was verbose with buddies in emails, so I could like kind of pull back. So This one was particularly tricky because of the startup nature, but some of the other projects that I've done, I make it a point to do just a quick phone recording of something, just as kind of like this is when I was first doing the drum feedback stuff. I'm like, oh, this is a kind of all right. Let me film a bit of this, and like this is kind of interesting, and then I just carry on. So I try to not interrupt my flow of feedback loop research, but still kind of take snapshots as I go. And because I'm either collaborating or for myself making notes, there's often email or chat things that end up as like text artifacts that I can then go back and parse. And because I personally like blogging or making videos or making explanations, there's a point at the end at which I then bring those together, which can sometimes be tricky because I can take these snapshots, I can take some text, and then if I don't do a blog or something about it at the end, they just kind of float in nowhere. So having snapshots that don't interrupt my flow as I go, but like quite a lot of them, more than I would need, then consciously summarizing those and synthesizing them into generally a blog or video. When I did my thesis, it was a little different because the scope of that's obviously a bit bigger, but it was many of those mini ones forming the big one. That kind of answer?
Yeah, sure. Like blog posts there in your website.
Yeah.
Okay. Yeah. That's great. Thank you.
Yeah.
It's super interesting, and I have to say I'm incredibly impressed with how much you got out of that position location technique. I think that works a lot better than I ever expected it might be able to. One kind of high level question is, how do you decide what matters when you're designing a system like this? Because I mean, you could keep on chasing better and better precision of spatial location for that. I mean, you can achieve lower and lower latency. It might be that to make the system playable, there's a certain point at which it doesn't necessarily matter that it's more precise in either a localized or globalized sort of sense, but maybe something else matters. Maybe you discover some peculiar behavior along the way that isn't what you intended it to be, but actually ends up making something super playable. So how do you navigate that as you go along to kind of know when to step back from the kind of precise engineering goal to say, hey, this thing is cool for what it is?
It's a multi-layered answer, and one of them is that like there's a temporal window at which perceivability, like the sort of 10 millisecond, 5 millisecond, like whether it can happen that time or not is like a binary, like, so if it's not yet happening that time, make it happen that time. So there's like, but once it's within that window of like simultaneous, I can do a thing and hear a thing in a maskable way, that then like from there, the diminishing returns gets fun, but less important. So it becomes more of like, is it then a compelling creative use case? And for me, there's there's that temporal boundary that's kind of always there. Can it happen within this time? And if I can't, how can I make it do that? And then the other one is that I have very finite engineering knowledge and capability of which I can't exceed, or I can only very minimally exceed with knowledge of people around me. So like without that paper as a jumping off point, this would not be possible for me at all. So like that, it was me extending beyond my own capability with what was available to me. So there's that as a hard boundary, in that like at some point I personally probably can't make the latency on that any lower. So like that's that. Like I can't chase that one anymore, even if I wanted to. And then beyond that, because here it isn't shown, and this one is particularly weird because in order to get all this to work, I needed a physical setup on the drum, multiple mics, I needed control and condition. So most of this testing and research was done with sets of audio recordings that I've accrued and then just did a ton of testing on. So this hasn't yet worked its way into like my iterative perform with it. Okay, this is kind of the end, want to adjust. Most of the other things I showed the instrument-wise, that feedback cycle was tiny. Oh, I want to have a fader on the drum, get an Arduino, do some stuff, get a code. Okay, that's cool. Okay, now I need this, and now like that loop is tiny. This loop is like years.
Now that I think the idea of how big or how small the loop is of playing and iterating is an interesting question in general. On the specific point around latency, one thing that came to mind is you have two things probably that matter. One is the absolute latency, and then of course the other is the variation or the jitter.
Yes.
And I wonder if there's actually a case once you get to playing this in real time where you might want to actually make sure that the latency is constant, i.e.
Yeah.
choose a worst case,
Yeah,
make
yeah.
all hits respond exactly at that time, so you don't have the feeling that hits in the center are actually a bit laggier than hits on the outside.
Yeah.
I mean, it's the kind of thing you probably just need to feel,
Yeah,
play
yeah.
it and feel how it goes.
I think this
but
is one of those cases because like this, so I can compute inner onset timings at a fixed window. So first onset and then at 128 samples, take the numbers. So that would be that kind of thing. Or I can, once I've received the fourth number, and it depends on what those feel like. And yeah, like that is a good point. And one thing which is a side product of this approach is that for my general descriptor analysis and audio classification, all these things, the having multiple sensors means that the latency, so like if I only have one sensor on the drum and I hit the drum here, there's a latency in the order of milliseconds before the sound even arrives to the sensor in a way that is generally not computed because just the speed of the membrane. Whereas with this, like that's cut in, like the worst case here is smaller because there's always a sensor nearby. But yeah, I mean, things like that I haven't yet, with this one that loop isn't closed yet because I need to now play with this, but like, yeah, I haven't really drilled down to that level of touch with it, but like I am curious to do that.
Really cool, fantastic work. I'm really impressed with the almost zero latency.
Oh, yeah.
Position detection.
Mhm.
Fantastic. Yeah, my question is a little bit more around instrument design because I think you are definitely a really good engineer. Maybe you don't say that, but what you have assembled here is a great, work of engineering. But yes, it really shows that you are also a drummer, and that's why you are chasing, up to the last millisecond because you can perceive it, right? And maybe there's musicians that they cannot perceive like the difference between, I don't know, like 2 milliseconds and 5 milliseconds or whatever. Anyways, my question is more about like instrument design and about how it looks that you seems to be always in control of the instrument, even though you have said that you are using feedback or something like that. Your instrument, all the different iterations that you have shown us here, they all seem to be really at your fingertips, right? I didn't see that this kind of like semi-stable, states, right? Where the instrument sounds by itself. You can drive it at a point where you can stop doing anything and the instrument sounds by itself, So I'm just wondering, what's your take on that?
Yeah. So I think it's a couple things. So like maybe like the first video I showed, like where it's like all these things going on with the drums, like I think that's a byproduct of one, having spent most of my life as some kind of instrumentalist or another. So there's a technical encoding of facility in my body and synapses that's just present from 10,000 hours on piano and on guitar and all that. So like there's an amount of facility that can just happen, which enables my synapses to do things. And then because core to how my even like conventional instrumentalism was, I was a multi-instrumentalist, my ability to rewire that was already broad. So be able to think on the piano, be able to think on the guitar, be able to the drums. I was able to often repurpose those things, which meant with a lot of novel instruments, unusual instruments, there's a lot of like stem cell synapses, not really obviously, but like I'm able to repatch like, oh, if I move this microphone like this, I get feedback like that. There's a metaphor that I can kind of tap into. So I think some of that is a byproduct of just having lived the life that I've lived. And then beyond that, I think there's some thoughtful design in terms of like building chaotic systems with hooks that are manipulatable. So I as much as I love pure noise and really wild things, I'm not super interested in having like, it's just crazy and I'm like doing a thing. Is it doing anything? I don't know, but I'm like I kind of like having it's doing chaotic things, but I have a gestural or a spectral or a temporal control over them in a way that's built into my conceits of instrument and software design, if that kind of makes sense. And then that couples with the first bit. So like there's some of it that's just here, and then there's some of it like I want to be able to do these things. And then when those come together, because some of those things they are chaotic, it is feedback. It is triggering things in a way that I don't really know, but like it doesn't feel that way when I'm doing it,
Great. Yeah, it's a state of control feedback, at least not by the instrument, but by you, right?
Yes,
You're always in the loop of that feedback.
Yes, very
Really
much.
cool.
Yeah.
Fantastic.
Yeah.
You mentioned when discussing the cross correlation that it was might be possible to use that with your sort of continuous interaction. I was wondering how much have you tried that or thought about that?
I've not tried that fixed yet, but the issue and why I abandoned it was because it requires kind of a slightly bigger window. But for friction, like non-onset based things, whether I'm here, like the window of time, like that's not really a perceivable latency. So that is intrinsic to that representation. The one thing I need to test with that is to see how much I need to filter the signals. Because with cross correlation, if I'm not touching the drum at all, the cross correlation is probably going to be a bit wild because it's cross correlated on noise. So then if I touch the drum, it will probably cross correlate to the correct place. But then if I go quiet for a second, does it return? So I'll need to be thoughtful with how the signals are filtered to make that a playable thing. So as I move around, it follows it without much latency. And then if I let it go, it doesn't just do garbage. So there'll be some real-time sensor smoothing oriented optimizations and experiments I'd like to do to make that happen. But I can see it be very plausible just to kind of touch and then just move. And then that's the use case for cross correlation. That's like what it's meant for.
Yeah, awesome. Cool,
yeah.
Thanks.
I have kind of more of a practical question. So I'm someone who also identifies with coming from more of an like artistic background as a performer, as opposed to like an engineer or whatever. This feels very mathy to me.
I apologize.
And so I'm wondering, as someone who, you know, you have a vision and you want to realize that vision, but sometimes there is a little bit of learning that has to take place as well.
Yeah.
How do you kind of like combat the two?
Man, I've been lucky that I have a lot of smart people around me, and I've been around a lot of smart people. And in these last few days, that's been a lot of that, where that thing of even just mentioning with the paper, there's like, my knowledge is small, like obviously on a human scale, like everybody's smart, you know, but like I look like I know more than I know. And a lot of it is because like I have a lot of smart people around me. So like even just chatting this morning, it's like, oh, that's really cool. And I have a type of personality disposition that's very obsessive compulsive. So I have a lot of like, I'm going to get to the bottom of it, you know, and so I can do that off little nuggets of like, oh, there's math in the quadratic. And it's like, what do you mean? That's a thing? And then I can do the grunt work to kind of try to make that happen. And then just being around in an environment where those kind of people and ideas can bubble up enables me to, you know, do the kind of grunt work at it.
Makes a lot of sense. I'm the same way. I obsess. And yeah. Okay. I appreciate that. Thank you.
Mm-hmm.
Yeah, sounds good. Yeah, thanks, Rodrigo. This is really, really good. And yeah, you definitely downplay your engineering abilities because you are a great engineer. I guess I wanted to pick up a little bit on Andrew's question of the sort of like engineering-based approaches and knowing when is good enough. And say, looking at a couple of examples, you had one with the DJ fader, and you decided that the resolution wasn't good enough based on a very particular application of using feedback and needing more resolution to control feedback. And so that was like, you know, grounded in this application you had in mind. Whereas I'm curious with the location sense of stuff, the drum location, is there like that application in mind where you know you need a particular resolution? Like, how do you know when is good enough?
Yeah, with that one, some of that was a bit of like sensing and intuition. Like I don't have a screen. It'll take me a second to put up a screenshot, but a possible use case for this as well is to have a under projection from the drum to physically illuminate on the surface, for example, a corpus or some sort of like playable space. And I'm trying to think it would be meaningful and required to be able to accurately tell whether I'm here or here. Just because in this amount of overall space, if I have like some kind of blobs of like corpora and like, you know, UMAP projection, I could very plausibly see that being a meaningful differentiation. So some of it is like proportional to this drum. I probably need 2 millimeter resolution or 5 millimeter, like something in that order to make that differentiation meanable. And just some of it, like knowing on a drum, if I play a little here or there, I want that nuance to be there. As whether it should be sub-millimeter, I'd want it, but maybe won't get it, but like that's fine. But some of it is like a bit of intuition of like the space and some of intended use cases. Like for example, on the physical model, the difference between those are very subtle. But if this is a UMAP projection, this is one sample and this is a completely different sample in a way that like that differentiation needs to be physically there.
Cool.
Projection from the
Like it looks, it's a little beyond my knowledge, but like there are pico projectors is a thing, and then there's short throw projectors, which and then there's pico short, and it kind of works, but like there's a snare stand underneath, so you have to be like with a mirror, and like it's a little beyond my knowledge, but I have a feeling it's possible, but yeah.
You're getting into photography.
Yeah.
Great. Okay, I think we're gonna wrap up there. So Rodrigo, thank you so much. Really, really appreciate the time. And thank you to everyone online. I'm glad you made your way to the new link. Thanks so much for joining.